Let's get a show on the road. Questions on homework? I think chapter 10. We finished 10 last time. What does that say?
Oh no, that one's right. This one.
I got the C, but
1, 2, 3, 4, 5, 6.
Okay, so A.
13. You wrote 12 of them. It's 14.
So I think we have these two. Yeah,
That's what happens when I write it out of quarters.
Like I see in the line where people are sitting on top of their shoes.
Oh no, I
Or when you're in.
Are you serious? I took mine off and my socks are wet.
Okay, well, wear a shoe that's appropriate for the weather.
Alright, let's buy them for me right now. Is it
Wear
really?
glasses on your
The bodies even still have emotions there.
No, it's okay to keep them on. I mean, I have no say in it. It's like I go into Starbucks, people say they're without their shoes.
I like it when like someone has like coffee and then
Fuck your shoes.
I'm wearing my socks, so
Yeah, you're right.
I knew I was right.
I didn't count these two for some reason. Why?
Okay, so let's do this. How do we write this as probabilities?
0.6.
T,
0.6.
parentheses, 5 plus, designating 5 over 5 years.
Okay. Well, we didn't do random variables yet, but here I can just sort of naively introduce it. How about we call it a variable? Let x be the number of years. So you can sort of write this down as something like x greater than 5, right?
Yeah, or equal to.
Sure. Well, it was phrased as more than 5. So, yeah, x greater than 5 is
0.62.
0.62, right? So it has to be a value between 0 and 1 that describes the chances. For x greater than 10, it's just 0.5. Part B, Bob. What's the probability that you survive between 5 and 10 years?
You subtract
62 minus 41.
Come again?
62, or 0.62 minus 0.05.
Yeah, 0.62 minus 0.5. So that would be what? 11.
111.
All right, so the idea is you can sort of just subtract them. So we know that up to 61% survive up to 5 years, but only 51 up to 10 years. You just find the difference between these years. Other questions?
Yeah, 12.
A. Bowl contains three red balls, two black balls. Well, the first one is sort of explain why probability of a red ball is 3 out of 5. Probability of black is 2 out of 5. B. Without replacement. Is after tree diagram. We're using red 1, red 2, red 3, B1, B2, AC. In the next section, we'll have a more efficient method of actually finding these probabilities, but for now, we're going to use the tree diagram. At least one is black. At least one is black. Okay, so part A says to explain in terms of equally likely events. Why are these the probabilities? P of R is equal to 3 out of 5 because assuming selecting any ball chocolate. It's probably the rain's fault. My bag got soaked. Okay, so this one is sort of this trivial thing. Basically, I'm using that theorem we talked about with k over n. If you have n ways something can possibly happen, there are k ways for what you want to happen can happen, then the probability is just k over n. This comes from the equal likelihood principle, and so basically that's that. That's not the main problem here. The main problem is drawing the tree diagram to figure everything out. And in the next section, we're going to actually learn how to do this without a tree diagram, because tree diagrams can get really big really fast. Okay, so we're going to do this a tree diagram. The levels are going to be the first choice and then the second choice, because we're choosing two, right? And we're choosing without replacement, meaning once we pick a ball, we cannot pick it again, right? We're not putting it back into the bowl. Right? So for the first choice, how many options do you have?
5.
There are 5. 1, 2, 3, 4, 5. You can pick this red ball, or another red ball, or another red ball, this black ball, or that black ball. Right? Now, assuming this is the situation, you pick the red, this first red ball, how many options do you have now?
4.
4, because you can't pick that one again. So you can either pick the second red ball, or the third red ball, or the first black ball, or the second black ball. Right? Similarly here, you can pick the first red ball, or the third red ball, or the first black ball, or the second black ball. Here, you can pick the first red ball, or the second red ball, or the first black ball, or the second black ball. Here you can pick the first red, or the second red, or the third red, or the second black. Here you can pick the first red, or the second red, or the third red, or the first black. So remember, when we counted how many things were on the last level, that told us the total number of possibilities, right? So we had 4 options, and we had 5 of those, so there are 20 total options. Total possibilities. So you can choose a red, then a red, or a red, then another red, or a red, then a black, or a red and another black, right? These are all your possible options for what can happen by making 2 choices. And so it says, draw a tree diagram. Okay, that's all we had to do. Now we're going to use this tree diagram to answer some problems. Part C. 1. The probability of a black and a black. What's the way you can get 2 blacks? You can go along this arm, B1, B2. That's the way to get 2 blacks. Or you can go along this arm, B2, B1, right? And that is the only way you can get 2 blacks, right? So we have 20 total choices. There are only 2 of them in which we have 2 blacks. Just by counting the arms, that's just 2 out of 20. Equals 1 out of 10, or you can write 0.1. Either of these are fine. 2. At least 1 is black. How would you do that one?
There'd be 2 up, graph 1, but B1, R1, B2, or plus. So it's 2 choices there, 2 choices there.
You have 2 here, you have 2 here, you have 2 here, you have 2 here. And
2.
1 here and 1.
1 there.
Wait, what is for number 2? So at least 1 is black.
At least 1 means 1 or more.
So what did it be? 2, 2, 2, 4.
So
4.
here's where you get 1, 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 here's where you get 1.
Then what did it be? 4.
All 4.
Then you have all 4 here because of
Yeah.
this. You have
All 4.
all 4 here because of that.
So 14.
So that's 14 in total.
Yep.
Probability x equals at least 1 black, greater than or equal to 1 black. We have 14 out of 20, which is 7 out of 10, or 0.7. Right? Just by counting how many ways at least one of these bees can be along an arm. Right? So we have 2 here, 1, 2, 3, 4, 5, 6. You select a black ball here, so every option here, so that gives you 8 more. Both are different colors.
So 2.
So from here we can have two. We get a red and a black, so that's two options there. So probability of different colors equals, we know the total has to be 20. So from the first arm, 1, 2, we have two options from the first arm, plus 1, 2, two options from the second arm, plus 1, 2, right, a red then a black, a red then a black. It's another 2 for the third arm.
3.
And so here we have 3, can have black then a red, black then a red, black then a red. So we have 3 here.
3.
And then 3 again, black and a red, black and a red, black and a red. So we have 3 here. Right. So that's what, 12? 12 out of 20. You can take 4 into each, 3 over 5. So once you figure out how to draw this diagram, now it's a matter of counting how many arms give you what you want. Any questions on this yet?
Should we be writing the probability in fraction form or decimal?
I don't really care. As long as it's between 0 and 1, it's forgivable, whatever the format is. Yeah, I'd accept either version. You can write this or this. Coin is tossed 5 times in succession. Probability of at least one head and at least one tail will appear. B, probability streak of 3 or more consecutive heads. Okay, all right. So for this one, I wouldn't really do a tree diagram. It's going to be crazy. You'd have 32 guys down here and 5 levels. You could do a table, but that'll also have 32 rows, so I don't really recommend that either. So I'd probably think of this a little more sophisticated. We can use the multiplication rule to figure out the total number of choices, right? Total number of possibilities. Use by the multiplication rule. Sure, you can do a tree diagram if you want, but it's going to take a long time. Multiplication. All right, so remember we have 5 tosses. 1, 2, 3, 4, 5. So this is the first toss, second toss, third toss, fourth toss, fifth toss. Right? How many outcomes do you have for the first toss? 2. Well, 2. And so on for the second and the third and the fourth and the fifth. By the multiplication rule, this gives us 2 to the 5th equal to 32 total possibilities. Now we're going to assume equal likelihood, right? It's equally likely to get a head or a tail, which means the probability of each is a half. And so now we just want to count the number of ways we can get what we want, and that should be out of 32. So how would I figure out the probability of at least one head and at least one tail?
I think doing it reverse is better, like what are the possibilities of not getting any heads or not any tails?
Right, in this case the complement is actually a lot easier, right? This is using the complement probability. This is just 1 minus the probability that you get no heads or no tails. And we actually did this multi-stage experiment thing, so we know that the or in a multi-stage experiment translates to a plus. So what's the probability of getting no heads? There's only one way to get no heads, right? It means you get all tails. So that's 1 out of 32. Probability of getting no tails means you get all heads. There's only one way for that, right? So we can reduce our counting by counting what we don't want in this case. It's a lot easier. Because figuring out at least one head, you have to figure out how many ways can I only get one? How many ways can I get two? How many ways can I get three? How many ways can I get four? How many ways can I get five, right? There's a lot of counting, right? Counting the opposite, where you get less than one, right, which is the opposite of greater than or equal to 1, meaning 0, is a lot easier. It's easier to count when I get no heads. There's only one way to get that, right? How do I get no tails? There's only one way to get that, right? So I just have those guys. So this is just 1 minus 2 out of 32, which is 1 minus 1 out of 16, which is 15 out of 16. All right, so those are the chances of getting at least one head or at least one tail. And here we use by the complement probability. So you're always sort of looking if this can help you. And you might be wondering why we didn't use something like that here. Well, it's because either way was just as bad. There was enough options on either hand. It didn't really matter. But here it actually matters. Like, it's easier to count how many ways to not get this than it was to count how many ways to get it. Part B is a little more tricky. Who did part B?
I just wrote out all the different ones.
32 of them?
Oh, no. Just the only ways to get 3 consecutive H. It ended up being only 8.
Okay. How did you start to write them down?
So I had 5 H's and then 4 H's. It was like a T at the end. You know, I set up like the different possible choices of what would happen out of, choice, first toss, second toss, first.
Okay, so you can set them up the possibilities. Right, so there was one where the street happens on, well, it starts, I should say, on the first toss. Right, so how many ways can that happen?
1, 2, 3.
Well, you can have 3 heads here, and then we don't really care what happens here or here. Or you can have so we only get 3. We could also get 4. We're gonna have to be careful we don't double count something here. And we can also get 5.
You can also get
Right. This one sort of.
There's one more opportunity here, though, right? Because if the first 8 is ahead, oh, I see. Never mind. Right. I see. If
The
it's
street
in the
doesn't
first,
have-
right.
Oh, yeah. So,
You're right. Sorry.
Yeah, so how many ways can each of these happen?
2.
Well, for this way, there's
There's 2 possibilities there.
But the possibility is also that last one.
Right, so here, this could be a heads or a tails, but in the case that it's a head, it's already counted here. Right, so this is, it's one way, right? This, we only get one new way, right? Because if this is an H, it's just that, so it has to be a tail. So pretty much you could replace this star with a tail T if you wanted to, because the other option is counted here.
That's one.
What about here? How many ways can this happen?
But the one of them is the bottom one. So it has to be only one
There's
way.
only one way.
Yeah, there's only
Right,
one
so
way.
this can be H or T,
Oh, no,
right?
it could be two ways. It could,
Yeah.
right? It can either be TH or TT.
Right, so the possibilities are here, I can get a T and an H or a T and a T, right? So there are two ways here. Right? So in total, for if the streak starts on the first toss, there are 4 ways for that to happen. Right? So let's pretend the streak starts on the second toss. Which means the first guy has to be a T, then I get 3 heads. Then for the last possibility, what will happen? Right? So there are 2 ways this can happen, right? I can have either a tail here or a head here, and I still have it, so there are 2 ways. Or
Only 2 ways.
right, there are only 2 ways.
Yeah.
We don't really have anything. What a, do you have anything else? No, right?
Yeah.
Streak starts on the third test. Which means we have 1, 2, 3, 4, 5, and the streak will start here. And now what are the possibilities for the first two?
2 ways.
I can have a T and a T, or I can have a T, an H and a T. Right? The case T and an H is already covered by here, right? So this gives us 2 ways. So in total, how many do we have? 8 ways. Eight out of 32. Which is 1 out of 4. Or if you want 0.25, like I said there. So like I said, with probabilities you have to really be careful. Sometimes you just have to map things out, use diagrams to help you, and so on and so forth. In the section coming up, we'll find ways to just attack these directly with algebra and arithmetic. But for now, this is what we know how to do. Just use diagrams and sort of picture it out and map it out and count carefully. Any other questions? We don't have time for like one more. Okay, no? Okay. Let's move on to chapter 11, class. Let's start to get a little bit more sophisticated because we don't want to have to draw tree diagrams all the time. Especially when the possibilities get very large. probability 2. So chapter 10 was a very elementary discussion of probability. Now we want to get a little bit more sophisticated because, you know, a lot of things have a lot of possibilities. We want to be able to get to the answer without having to draw out all these diagrams. Although there are situations where diagrams are still very useful, but we don't want to have to draw them. We start with two very important definitions. What do I want to tell you? Mutually exclusive and independent definition. Two events, A and B, are mutually exclusive if they cannot occur at the same time. Right? So one happening excludes the other happening, right? You call this mutually exclusive. I.e., if you want an equation that describes the situation, the probability of A and B is 0. It's impossible for both to happen at the same time, right? So A and B cannot happen. Example. By tossing a coin once, the events H and T are mutually exclusive.
Unless it lands on its side.
Right. Unless it
That's
lands on its
neither
side,
nor
which
that's neither H and nor T. So
yeah, that's like some.
still exclusive. Unless you have a misprinted form.
Oh yeah, then we go ahead.
Two level things.
All right, you flip the coin to make it flat. Okay, in that case.
Then you're affecting that.
So that means they're mutually exclusive when they cannot happen at the same time. So in a single coin toss, the probability of getting a head and a tail is assumed to be 0. Right? You can't get a head and a tail. Right? It has to be one or the other. If you get a head, it means you didn't get a tail. If you get a tail, it means you didn't get a head. So, second important definition is that of independent. Two events, A and B, are called independent if one occurring does not affect the other occurring. An equation that describes this situation is P and B is equal to probability A times probability of B. You can sort of think of it as a multi-stage experiment in this respect, right? One just happened and you have this many options, and then you have to multiply it by the options of the other one. Just think of it as two different stages. So, yes. The blinds. Is that better? So, I've seen students mix these two up all the time. They're not the same thing, right? One means and is 0, and the other means and is the product of the two probabilities, right? This is independent. it's when they're the product. Mutually exclusive means they cannot happen together. So they're two very different situations. The thing is, so before when we were doing chapter 10, and we sort of said, oh, we could replace and or with different probabilities. Oh, I should probably do that on these. Maybe not. I'll mention it when I get to that. Okay. Well, I'm going to mention it now, actually. If A and B are mutually exclusive, then probability of A or B is just equal to the probability of A plus the probability of B. And this just comes from a simplification of a general formula I'm going to be giving you soon. Right? Mutually exclusive, this works. Another rule that I can give you, if A and B well, I actually repeated this rule, are independent. This is worth repeating because of mistakes I see students make all the time. I want to make a disclaimer here. It's a very important disclaimer. Maybe 2 asterisks. Highlighter. Underline. I should have colored chalk. Anyway, these equations are not true in general. They work only in the situation specified. Big common mistake students always make. They just always think, oh, probability of A or B is just you add the probabilities. No. Only if it's mutually exclusive do you add the probabilities. Not in general. If you do not know for a fact it's mutually exclusive, do not assume or means and. You can only do that if you know it's mutually exclusive. Unless you know for sure they're independent, do not assume that the probability of and is multiplied. That only works if they're independent. It does not work in general. What always happens is I always give these equations and people think, oh, it always works. Let's just always do that. It doesn't always work. Be very careful. Only in these 2 cases. You have to be sure that the things cannot occur together. Then this is true. And if one does not affect the other, then this is true. By the way, I should probably give you an example of independence. So if you do this experiment, you flip a coin and then you pick a card. right? What happens to the coin has nothing to do with what card you pick, right? They're independent. So if you had to say the probability, what is the probability that you get a head and you pick an ace of spades? You just multiply the probabilities. Right? It doesn't work in general. Okay, so I did my warning. So that's very important. We have these two equations. This one works only in the case of mutually exclusive. This one works only in the case of independent. So note these rules can be generalized. You can prove this with something like induction if you were in a more sophisticated math class, but just take my word for it at this point. Suppose E1, E2, E1. What did you say? I'm not saying you're not sophisticated, but the math we're doing is not. Are n independent events. Then, if I find the probability of E1 and E2 and then I can simply just multiply all the probabilities to figure out what that is. Suppose E1 to En are mutually exclusive events. Then E1 or E2 or also note, just give me a bunch of rules and then we'll do some examples after this. 1, 2, 3, maybe 4 examples? 3 examples. And then we move on to another topic. Okay, so in general, I'm going to give you some general equations now for events A and B. Probability of A or B is the probability of A plus the probability of B minus the probability of A and B. This is called the law of disjunction. This is a general equation. So the problem here, you can see why for mutually exclusive events you just have to add the ORs, right? Because this guy is 0. Basically the idea is if you're doing OR, you want to prevent double counting. So if the circles represents the possibilities in A and B, well, if A can happen, it's all of that. And if B can happen, it's all of that. And notice that you counted the middle, the intersection, twice. And so what you do is you subtract the intersection to get to be an A or B, but not both, because you'd have double counted. That's sort of the idea. And of course, in general, this can actually get, if you're considering 3 events, you know, an A, a B, and a C, then the probability of A or B or C
So just put each of them element.
or B or C, it gets worse as you get bigger, right? Is the probability of A plus probability of B plus probability of C. But you sort of have to subtract anywhere that would be double counted. So you have to subtract probability of A and C minus the probability of
B and C.
B and C, but not A, minus the probability of A, B, and C.
And A and B, right?
And A and B. Right? So the bigger you get, the worse it gets if you don't know they're mutually exclusive. Right? But this is sort of the idea, because you would be double counting unless these circles are completely separate. Right? When the circles are separate, you have mutually exclusive. Right? One circle doesn't. If something happens in A, there's no way it can happen in B, and so on and so forth. So those are the general formulas. And here's a fact that's sort of disturbing, in a computational way anyway. There is no general formula. So for OR we have a general formula, it's called the Law of Disjunction. For AND we don't really have a general formula. It's just one of those things that you empirically verify usually. If you don't have a way of figuring it out mathematically, then it's just like you run experiments in real life and you pretty much just count a probability by the number of experiments you're doing. You try to do enough to get an accurate idea, but that's basically it. So this is sort of why we know, for example, that the probability of having a boy and a girl aren't really the same, right? You can't just assume, well, there are only 2 sexes, so it's just 1/2. No, if you take the statistics, measure how many people have boys, how many people have girls, you realize girls survive more times, right? So the probability of having a girl is actually slightly higher than having a boy, and that you know from experimentation, right? So with AND, it's sort of the same thing. In general, you might have to do some experimentation. The only time you'll have a formula for this is when you know the events are independent, when they don't have anything to do with each other. Then you just, this is just probability of A times probability of B. Okay.
And it will always be indicated if they're dependent.
It will not always be indicated.
So what do we assume?
It will only be indicated if it's not painfully obvious. Right, so for example, like in the case of the example I wrote here, I talk about flipping a coin and picking a card, it's obvious it's independent. Like one has nothing to do with the other, right? If I'm talking about flipping 2 separate coins and then counting the sum of the total, then you're like, one probably depends on the other, right? So, and there are other times when we'll give you this extra information where we'd say, okay, here are these 2 events, and we know that the probability of them happening together, probability of A and B, is this number. If you can double check that, oh, if I find a probability of A and find a probability of B, I multiply them, I don't get that number, I know they're not independent. So in general, to find this, you'd need additional information. But there's no general formula for it. So don't just assume once you have this, you multiply them. That's not the case. You have to know they're independent. And unless you have a really good argument for them being independent, or I tell you they're independent, then do not assume this is the product. Examples. Let's see these in action. Oh, I'm thinking I should have typed these up a bit. It's another choosing ball. A bowl contains balls. By the way, very typical kind of problem to show up on a final. You're pretty much guaranteed to have a problem like this, where you're choosing something from a group of things. 5 are red. 4 are blue. 1 is green. select two balls without replacement, right? It's a very different situation if you select them with replacement. And what is the probability that both balls are green? Both blue, 3. Both are of the same color. Or spelled the American way. 4. Both balls have different colors. This is probability of green and green. Sorry about that. What's probably of getting a green ball and a green ball in the second one?
0.
How do you know?
If there's only one green.
Well, if you want to use common sense, geez, why were you? Okay, yes, it is 0. There's only one green. But if you try to do it the math way, it still wouldn't lie to you. The idea is, on the first pick, how many options do you have to get a green? You have 1 out of 10 times, so this is the first choice. And in the second option, now you have 0 out of 9 that are green for the second choice. And how do we know there's a multiplication here? The events are independent. Right? So if I pick a ball and I throw it away, right, it doesn't make any other ball here. It has no claim on what I pick second, because we have independent events. Right? So this is a case where they wouldn't really tell you it's independent. You'd sort of have to figure it out. Right? The ball I pick first has nothing to do with the ball I pick second. There are 2 different choices. What about the probability that both are blue?
4/10.
Okay, so there are 4 blue balls. So the first choice is 4 out of 10 for the first choice.
Times
3
And
3 out of 9.
now I only have 3. I only have 9 balls remaining because it's without replacement. Means once I pick a ball, I throw it away. Now there are 9 left. And now there are 3 blues because I already picked 1. And so for the second choice, I only have 3 out of 9.
So 2 15s.
Right, so this is 2 out of 15.
Oh, I see.
Right, so you just 2 into this goes 2, 2 into that goes 5, this into that goes 1, this into that goes 3, so 3 times 5, 15. Okay, so probability part 3. From 3. What if they have the same color? How do we do that?
So it's like the probability of all blue, probability of 10, probability of.
Right, probability that we get 2 blues, or we get 2
Red.
green,
Red.
or 2
Okay, I
red.
have two.
Two red.
2 red, or you get 2 green, right? Now, why is it or?
So dependent.
No,
Mutually
independence on-
exclusive.
They're mutually exclusive. If I pick 2 blue, I couldn't have picked 2 reds because I'm only picking 2, right? There's no way this and this can happen. I can't say I choose 2 balls. Yeah, 2 of them were blue, 2 of them were red. What? No, you can only pick 2 blues or 2 reds. They're mutually exclusive. If this happens, that didn't, right? And this didn't either, right? If this happens, this didn't, or that didn't, etc. Right? So these are actually mutually exclusive. Like I said, this is the kind of problem where they wouldn't say, oh, notice it's mutually exclusive. They're not going to tell you. You sort of have to figure out, oh yeah. But this and that could not happen at the same time. I couldn't pick 2 blues and 2 reds if I'm only selecting 2. Right? So 2 blues we found earlier, that's 2 out of 15. Or let's just rewrite. 4 out of 10, so that's my first choice, times 3 out of 9. So that's the way to get 2 blues. Or, how do I get 2 reds?
5 out of 10.
There are 5 choices out of 10. Now there are only 9 balls left, and I have 4 out of those that will be red if I threw away the first red. Plus, the probability of 2 greens we already found was 0. And so this is 12 out of 90 plus 20 out of 90. So this is 32 out of 90. So this is 16 over 45. So you see, equipped with those 2 formulas that we have, we don't really now have to like draw the diagram and sort of figure out what's going on. We can sort of tell, oh, well, we have a case here where we both have independence and mutual exclusivity. So, boom, right? I can just multiply or add the probabilities depending if I want an and or an or, right? You get 2 blues, I need a blue and a blue. Or a red and a red, etc. Right? You can literally just replace these with mathematical operations. We have the 4th case. What is the probability of different colors?
The probability of not getting different colors.
1 minus the probability of the same color. This is just 1 minus, well, we found that in the last step. 16 out of 45. Right? And that leaves us with what?
29 versus
29 out of 45. So probably different colors, we can say, what if we get, right there, this is one of the cases where you know, why would you choose to do that? Because the other way, there are too many options, right? You can get a red then a blue, or a red then a green, or a blue then a red, or a green then a blue, or, you know, you're like, oh, I have to count all these ways. No, different colors is the opposite of the same color. I went through the work of finding the same color, so just subtract it, use the complement. Right? It's easier to count this than it is to count the reverse. Because then you'd have to worry about switching the order, right? If I pick the red first, why if I pick the red second, you know.
and there's 2 different reds.
Yeah, there are 2 different ways to choose a red for any given possibility. It just gets crazy. So whenever that happens, you start to think, well, what if I look at the opposite, right? Because figuring out directly it's sort of nasty, right? So that's sort of a hint when you want to use this, right? Counting it directly is like, oh, there are too many ways, and what if this happens? What if I have to switch to, Then you try to think, what about the opposite? Oh, well, wait a tick, I calculated the opposite over there. And then you just subtract. Any questions on any of this? Pretty straightforward. So, yeah, and there's always a problem like this look at every final for like the past 5 or 6 years, there's one of these problems on it. And they usually only ask you about choosing 2. The only thing that might change is with or without replacement. Then things get a little bit different, but not totally different. Did I actually do that with or without replacement? Oh yeah, that was my second example. Repeat the previous problem. With replacement. Because I know some of you think, what if we replace them? Okay. Fine, I heard you. Heard you in the back. Okay, so if we replace them, how does this change things? Now we have probability of green and green. What is that? So there's one way to get a green out of 10, but then I put it back. So now it's 1 out of 10 again. So this time getting a green and a green is not impossible. It's not very likely, it's 0.01, but it's not impossible as well. So now it's actually possible to get 2 greens if I'm replacing it, right? Before it wasn't. Because I pick a ball, and then I put it back, and then I close my eyes and I pick another one. So the denominator is not going to change. It's always going to be choosing out of 10, because every time you make a choice, you put the ball back, you mix them around, and you pick another one. The second thing was, both are blue. Okay, what's that? 4 out of 10, and then you put it back, so you have the same option to get it again, 4 out of 10. So this is 16 out of 100. 4 out of 25. I think this was probably the same color. And this is probably of blue and blue, or red and red, or green and green. Probably of blue and blue. Right. 4 out of 10, 4 out of 10. Right. So it's blue and blue. It's independent, so and can be replaced and multiplied. Probably of red and red. 5 over 10 times 5 over 10 plus probably of green is 1 over 10 times 1 over 10. So this is 16 over 100 plus 25 over 100 plus 1 over 100. So what is that? 42 over 100. 2 into that goes 21 out of 50. And 4. Probably a different color altogether now. One is probably the same color. Leaves us with what? Alright, just think of this as 50 over 50, 29 out of 50. Can't simplify. Questions? Okay, so at least I did these two for you to appreciate the with or without replacement thing actually does make a difference. Don't assume. That's why usually in the question they'll underline with replacement, without replacement. But even if they don't do that, be sure that you read the problem carefully and you figure it out. Okay. Another very typical type of question, which We're going to get more sophisticated with it after we do chapter 13, but just to start getting familiar with it, it's a question about blood types.
I'm so excited.
The problem of this type you get on the final, if one comes up, will be more complicated than this, but after we do chapter 13, we'll deal with the more complicated case. For now, let's deal with a case that we can deal with in chapter 11. The probability of having blood types O, A, B. So in general, we consider there to be 4 blood types. Probability of A is 0.4. Probability of B is 0.1. Probability of O is 0.45. Probability of AB is 0.05. Right, so probabilities like these come from statistics, right? They basically tested a lot of people, and they're like, well, like 4 out of 100 people, 4 out of 10 people will have A, 1 out of 10 will have this, 45 out of 100 will have this, 5 out of every 100 will have that. Right? So they pretty much, these probabilities came from statistics, right? This is sort of showing you the linkage between the two. Sometimes to figure out these guys, we need statistics, and sometimes to help us compute things in statistics, we need these guys. So it's a very reciprocating relationship. Okay, there's also some more info that you need. There is a blood protein called the Rh factor. There are 2 types. There's Rh plus and Rh minus, with the probability of having this blood protein or that blood protein is, one is far more likely than the other, 0.85. The other is 0.15. And these probabilities hold within blood types. Okay, so now we're going to figure out, if you're a doctor on call, what is the probability you're going to have to give someone bad news if they need blood? Well, you know, on a Tuesday during this time of the year, we usually have this many people coming in to donate blood. So yeah, it's likely that we won't be able to give you the blood you need, right? What are the chances that that's going to have to happen? Hey, it's something you have to prepare for, right? You just need to know modifications. A man with blood type AB an Rh plus factor needs 1 unit of blood. After being in a terrible accident or something, right? So only 1 donor is needed, right? 1 person can just donate 1 unit of blood. Only 1 donor is needed. When we get to chapter 13, we're going to pretend, oh, what if we can have several donors, and how many people will show up, and blah, blah, blah. More complicated. Only 1 donor is needed for this much. It is also known, we have a curious fact that helps a lot of people out. It is known type O can donate to any other blood type. And a donor must have the same RH factor. So to be able to donate blood type with someone, you first have to have the same RH factor, and you have to have either the same blood type or blood type O, right? And through medical history, we figured this out, hopefully with not too much trial and error. What is the probability? That a random person could donate blood to the guy? There's no blood left in the hospital. You run out frantic to pick a random person off the street. What are the chances he has the blood you need? B, if 10 people donate blood that day, what is probably the man will get the blood he needs? In other words, at least one person can donate blood. Last example for this section. Okay. She's just writing down the question for okay. So it's also very typical to get either a blood type question or one very similar to a blood type question on a final. So this is something that's important for you to know. Okay, so do you have all this information?
Yeah.
Well, I'll probably need to ask you. So if this question is asked, they'll give you all the probabilities, so you don't really have to memorize them. They'll tell you what the probabilities are, and then they'll ask you a question like this. Okay, let's do part A. So what's the probability that a random person could donate blood to this? What do we need?
I think the probability of AB times the probability of RH positive.
You need AB and RH plus, or
Oh, and RH.
you need O and RH plus, right? Those are the two cases in which someone could donate blood to this person, right? Now we use the two rules. These are independent, right? If you have a certain blood combined with a blood protein, well, your blood type doesn't depend on the blood protein. The blood proteins permeate all the blood types. So this you can think of as AB times the probability of RH plus. Because it's really, they're independent whether or not you have one. Or is mutually exclusive because you can't have a person having two different blood types. Either your blood type is AB or it's O if you're in this situation, right? You can't have, my blood type is O, but sometimes it's AB. You can switch. No, you can't switch, right? You can only have one blood type, right? So this is probability of O times the probability of RH plus. So,
Well, I mean, yeah.
what? What did you say?
You're right. But
What, you have two different blood types?
It's not
technically,
real
you can
rules,
also
this is how
donate.
it works.
You could also what?
A or B can donate to person. Actually, no, you can't. That's not true. You can't. Because then the person with
I asked you a
A
question.
has antibodies for B. No, you aren't. But O negative can donate.
O negative can donate to anyone, it's the go-to blood type.
Really, if you're O
But-
negative? Or just negative?
Anybody with a negative can donate to their blood type of a positive because it's about not having something, so it's not going to affect that person.
Yeah, it was written by a math person, not a bio person. So I don't know how much research. Well, this is the information we were given, and usually in the textbook, this is how you. I don't know. Maybe you can look it up. Maybe it's true. Well, if that's the case, you would know, and now you know all the math behind it. You'll be able to figure out, the real situation, the real truth. Okay, how do we do this? Probably of AB. 0.05 times 0.85.
Yeah.
This was what? 45?
AB positive is B
And what was that?
versus
0.425. Everyone agrees?
100%.
Okay, so that's probably that a random person can donate, right?
100%.
Not 100%.
Google it.
So, so basically, what you can interpret this number by saying something like, if you run out there, you get 1,000 people, right? Around 425 of them should be able to donate blood to this guy, right? So if you have time on your hands, just run out there, try to start grabbing people off the street. We need your blood, okay? And you're actually a little less than half as likely, so to get it from 1,000 people. Okay, part B. 10 people can donate blood. They can each donate 1 unit. This guy only needs 1 unit. And what is the probability that the man will get the blood he needs? Which means at least 1 of the 10 people can donate blood. How do we do that?
So the probability of it not happening meaning 0 out of 10. Right?
Yeah. So probability of at least 1 can donate equals 1 minus the probability that no one can donate, right? And this one is a lot easier to count than the other one, right? There's only one way this can happen. All 10 just don't have the right blood type, right? Where at least 1 can donate, you can say, well, only 1 or 2 or 3 or 4 or 5 or 6 or 7. But the first person can do it, but the second can't do it, or the second person can do it, but the first can't do it. And tons of possibilities here. But there's only one possibility for no one to be able to do it. So how would that happen? I'm using the complement probability by the complement probability. So remember what this is saying was the probability of what you want is 1 minus the probability of what you don't want, right? That's sort of the idea. And you would think to use this if what you want is really complicated, there'd be a lot of different situations. There are too many to count, right? You have 10 people and you want to know if either 1 or 2 or 3 of them or 4 of them or 5 of them or 6 or 7 or 8 or 9 or 10 can donate blood. You'd have to need at least 10 options. Within those 10 options, there are many ways, right? Maybe the first person can donate, or the second, or the third, or the fourth, right? And so to get to this directly, it's just too many options. So then you figure out, what is the opposite? What is the opposite that he doesn't get the blood he needs? It just means all 10 could not donate, right? There's only one way for that to happen. So it's easier to figure out what I don't want here. And so I'm going to use that, use the complement probability. Right? 1 minus probability that no one can donate, which means all 10 cannot donate. All right, now let's see who has their thinking cap on. How do I figure that out?
So would the probability that no one can donate be like the probability, the sum of the probabilities of everything except the other thing?
No, why would you think of a sum?
So like the probability of
Like if you have 10 people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What's probably that no one can donate? Like he cannot donate or he cannot donate? Is that what you would say? How do you sort of phrase it? How do we connect these? With what word?
And
It would have to be and, right? So the first person can't donate, and the second one can't donate, and the third one can't donate. Right, when you say or, you sort of have the possibility of maybe he can do it, but he can't, right? You want to get rid of that possibility, right? None can donate. He can't do it, no, and no, and no, right? So it has to be an and that connects all these 10 people, connecting 10 no's, right? It has to be and. None of them can do it. Okay, so now that we know it's and, how do we figure that out?
that's multiplication.
So what's the probability of not, right? That would become multiplication. What's the probability of not being able to donate? I know what's the probability that we can donate. Right.
5.
So the probability of can't donate is 1 minus the probability you can donate. And that I just found. So this is just 1 minus 0.425, which is point what? 0.575? So that's the probability that a random person cannot donate. Now, what's the probability that 10 people in a row cannot donate? Probability that none of the 10 can donate. This is equal to the probability that the first can't and the second can't and the third can't, etc. And all the way up to the 10th person can't. Okay. So this is the probability that the first can't. But blood types are independent, right? What your blood type is has nothing to do with what his blood type is, right? We're not even assuming you're related or anything.
Yeah.
So probability that the second can't times probability that the 10th can't. But these are all the same probabilities. So really it's just the probability of you can't donate raised to the 10th power.
So that basically.
Right, so this, we raise it to the 10th power. That's the probability that 10 people in a row cannot donate. So this means probably none of the 10 can donate is going to be 0.575 raised to the 10th power, which is
0.004.
0.004.
Yeah. I rounded.
Yeah, approximately 0.004. So this means the probability that someone can donate, at least one, is just 1 minus 0.004,
0.996.
0.996. So luckily for this guy, if 10 people show up to the blood bank, there's a pretty good chance that he'll get the blood he needs. So in this case, you can tell the patient, calm down, and you won't have to be lying. Right? That's great. Just like, don't worry about it. The chances of this working out for you is, yeah, don't worry. We have 10 people downstairs donating blood right now. There's like a 99% chance that you're gonna get it. Don't worry about it. Right? If that weren't the case, then you'd be like, well, you figure out what you have to tell them. I would suppose you get some sensitivity training or something. But that's not my sphere.
Try next door.
Try next door. We didn't finish chapter 11, but I'll stop there for now. And so, yeah, pass up your homework to chapter